All right, everybody. So thanks for coming today. Welcome to Hardware Interfaces Working Group meeting number 14. My name is Matt Robinson, and today we have with us John Wason of Wason Technology, based out of Tuxedo, New York. And he's basically the creator of Robot Raconteur, which you can see here, and has a lot of experience in developing interfaces for various types of hardware. And so he's agreed to share his experience, our series on different folks that have experimented with or created interfaces and their approaches. So John, the floor is yours. Thanks for coming today.
Thanks. My name is John Wason. I'm the owner of Wason Technology, and I'm also a visiting researcher at Rensselaer Polytechnic Institute. And today I'll be talking about the hardware interfaces and standards for Robot Raconteur. This is not the introductory speech. There's a link in the slides and in the invite for the introductory lecture. So this is going to focus in specifically on the hardware interface issues. So I do want to just give a quick overview, just to remind people of what Robot Raconteur is. So Robot Raconteur is a remote procedure call system, which has been enhanced for use with robotics automation. So its inspiration is based on Java RMI, Java Genie, which is a older technology, which has kind of a distributed interface between different classes of devices. And this technology kind of got overpassed by HTML and JavaScript, which is interesting. So if you haven't heard of it, it's worth looking into. .NET Remoting, which is similar to RMI, ActiveX, DCOM. So a lot of these kind of older, more business-oriented technologies. It's designed to be very compatible and to be technology agnostic. So it runs on many languages and transports and platforms, all the major ones. It's a client service model. And there's something called augmented object-oriented, meaning that we enhance the standard properties of object-oriented models to better work with automation systems. And it allows for forward and backwards compatibility using polymorphism. And I don't think I explained in this lecture, but I can talk about that too. It's plug and play capable in two different ways we'll discuss later. It's designed for request response, streaming, and most recent data. So this is more of a way to handle the type of data semantics you have in a robotic system. It has TLS for security, which is the standard encryption method. It has certificates for the nodes to provide authentication you're talking to the correct device, and has password and certificate security. It's compatible with web and cloud systems, so it's able to work with HTTP servers and web browsers. It has discovery. It has long-term compatibility. That's one of the main goals, is to make sure that we can talk to devices over long periods of time, since industrial equipment often lasts for decades. So you want to make sure that you can always talk to your equipment. It's open source. The first open source release of the updated software, it was in 2018. So this project has started in 2010, but the more recent incarnation was released in 2018. There's open standards. So this is a standard for the core of the system. In this repository, we'll talk about the other type of standards later. The core package is available in ROS Noetic and ROS Humble now. So this is available in the ROS library. There is a ROS bridge to talk to ROS topics and services using Robot Raconteur, and we'll get into a lot of detail about that later. And we use the standard types we developed to work with what they call the Pyre open source teach pendant, which is another project based on Robot Raconteur, which allows for easy programming of any robot, which has a Robot Raconteur driver. So on the right side, we have the image of our test bed at RPI, which has a UR robot, an ABB robot, and a Sawyer, which all run the same client software through the Robot Raconteur driver. So you can see there's a little box here running the driver for the Sawyer. And each one of these devices has a box. Now you don't need a separate box, but it makes it easier to deal with if each robot has its own computer running the driver. And then here we have the programming pane for the the teach bennett, which can either be in Blockly or a restricted version of Python. And then there's a physical teach bennett. So I don't want to go into too much detail now because this isn't too significant for this discussion, just an overview of the awareness of where everything fits together. I want to thank the contributors to the technology we'll be discussing. So this has been primarily a project between RPI and my company. So I was a student when this started up, and then ROS technology was created after I graduated to continue developing this and some other technology. And of course, Southwest Research has been involved the last couple of years, as well as General Electric and Raytheon. And the ARM Institute in New York State has provided a lot of funding for various projects. So ARM has, as I said, ARM has been a major contributor for funding. So there have been dozens of other projects beyond ARM projects, which is discussed in the lecture from ROS-I. If you want to go back and follow up on those and see what we've been doing. So 2 projects we completed is they provided a project specifically for Robot Raconteur where we developed these standards and some of the drivers, and also just worked on the core library itself. And then the follow-up project was the teach bennett we developed. And unfortunately, these were both hit by COVID, so they're not quite as developed as we had hoped by the end of them because of the pretty significant disruptions. We have an ongoing project for developing optimized robot motion programs, which will track arbitrary paths. That'll be finished at the end of the year. And then starting as soon as we get the paperwork done is another project at RPI for convergent manufacturing, and then another project with Raytheon for welding of composite structures. And then we had another one we submitted, which we were hopeful for, but didn't quite get through. We were close, but didn't quite make it for virtual commissioning. So we'll be resubmitting that in a future call. So just a brief overview of the convergent manufacturing project, which will be starting up soon. So the robot motion program track is open loop of trying to use feed forward planning to improve the accuracy and iterative improvement. So the goal of this project is to try to use sensing feedback to improve these trajectories. And this also involves using a WAM testbed, which is I can correct me if I have the wrong acronym. I believe it's wire arc additive manufacturing is the technology they'll be working on. So we'll be starting this up in the next few weeks, and this will be continuing until late next year. So this diagram is an overview of how Robot Raconteur works. So essentially, you have objects which live in the service, and the goal is to be able to communicate with them from the client. And essentially what Robot Raconteur does is it takes the objects and creates references or proxies in the client, which then receive commands from the client and forwards them to the service, and then returns them the response back to the client. And the contents of the objects are defined in what they call service definition files, which is an interface definition language, which define the objects, the value types, the exception types, and that's passed to the client on connection. And from that, Robot Raconteur can create the interfaces automatically, giving true plug and play behavior. Exceptions are passed using try-catch, so that if there's an error on one side, it'll be passed to the other transparently. So you don't have to worry as much about building your own ad hoc error handling system. And uses the augmented object-oriented model, which we'll go into great detail in a few slides. And you also have user-defined value types of structures, pods, and named array. Again, we'll talk about that in a bit. So there are 2 ways that Robot Raconteur handles plug and play. One is through dynamic type and proxy handling. So when the client connects, it gets sent the service definition, and the client can then generate a proxy to talk to the object. And this is used for scripting languages like MATLAB and Python. Or you can have standardized service definitions, which are basically static types. And for like a production device, you have clients designed to connect to specific types of devices. And if a service implements that service type, then the device can talk to it. And we develop standardized types to allow for this. So these are the 2 ways that plug and play works in Robot Raconteur. And of course, for commercial system, you'd want to use static typing. And dynamic typing is mainly for scripting languages and prototyping in laboratory use. So this is an example of a service definition, or what piece of service definition, I should say. The actual file is a bit more complicated, but the object is defined like this. You have an object like to create, and you have a function to drive, start and stop streaming data, and then what's called a wire, which is designed to give you the most recent value. And there's a custom type here used to contain that data. So for all the documentation, we use a iRobot create with a Raspberry Pi on it. And I believe that the Turtlebot 4 is now a create. So these examples should work on the Turtlebot 4. I built this back quite a while ago, and we're still using iCreate 1. So it's been around for a while. We've also done some work at DuckyBots, but I don't know if you have a kind of tutorial for that. And the enhanced member types contain a lot of semantic information about how data is communicated and how commands interact with the client, much more so than a lot of other systems which have a less rich object model. Let's look through each of the different members which are available. So for those who may not be familiar, in object-oriented languages, members are what are available inside an object. So for Java, or sorry, for C#, for instance, you have functions, properties, and events. That's kind of the standard observer model. And this is also implemented in like Java Beans. In C++, you have basically functions and fields with some variants of C++ having properties. So we have 8 different members available for Robot Raconteur, and these all provide very specific capabilities to the caller or to the client. So property is a standard get set synchronous operation. Although when I say synchronous, I mean that you request something from the service and the service responds. Although in most of the implementations, you can actually do an asynchronous call where you start the request and then receive a callback or future to get the result later. So just keep in mind that when I say synchronous, I mean just a communication method, not that you have to wait for the result in your software. So property is a simple get set where you have a value on the service and the object you want to receive, retrieve, or set. A function is a call to the service to execute an operation. So you can have 0 or more parameters and return a single value. You may also have a generator return, and if you use Python, you should be familiar with generator, where basically it returns an object which you have a next command, and you call next until you get a stop iteration event. Or you can close or abort the generator. And this next can either as an and or to have a return value or have a parameter sent to next. And this provides a way to have a very simple coroutine. And this is used primarily for transmitting large data where you may have like a large file, which is too big for the limit of the transport, which is usually around 10 megabytes per message. Or if you have a long running operation like an action, you'd use a generator. And the modifiers are not important for this discussion. They're just important for the service definition implementation. You have an event, which is basically a broadcast notification to all clients. You can also pass arguments with the event. And these do not have much flow control, so they're mainly used for rare instances where you want to alert all of the clients at once. An objref is short for object reference, and this is used to retrieve other objects within the service. So you cannot return objects from the other members. Objects are special because they are not serialized, while value types are all serialized when they're sent back and forth between the client and the service. So objects exist in a tree in the in the service and use a service path to figure out which object you want to talk to. And this is mostly transparent to the user, but there are a few times where you do need to interact with the service path to access the correct object. And then there's a pipe, and pipes create half or full duplex reliable streams between the client and service. You can also turn off reliability if you want to, but typically they're operating reliable mode. And you can create multiple connections between the client and service for each connection. And they have a callback, and the callback has like a reverse function, allows you to call a function on the client from the service. You must specify which client you want to talk to, though. And the callback does not support generators. And the wire is similar to a pipe, it only handles the most recent value. So this, if you want to track a position or the state of a device, this will only give you the most recent value. It's partially reliable in the sense that the transporters are expected to make sure you have the most recent value if the data stops being transmitted, but will not guarantee intermediate values. The wire can operate either in connected mode or peak mode. When you connect a wire, it will asynchronously send packets, either to the client or to the service, from client to service. And you can also peak and poke the wire if you want to do synchronously without making connections. So that avoids having the constant data flowing back and forth. You only need to have instantaneous value read or written to the wire. And then a memory represents a random access memory segment. When you call over a network, it will break up the read and write operations smaller chunks to avoid overflowing the transport. And right now it's not implemented, but this is also meant to represent a memory map mode. So if you have like a device at the register set or a large data buffer, the idea is a memory will represent that functionality. And as I said, in future implementations, it'll map it directly rather than having to use a read and write operation. And then there's supported value types, which is a very rich set of capabilities for values. And as I said, these values are always serialized, going back and forth between the nodes. So there are primitive types, your standard floating point, fixed point, and complex types, of course, string as well. You can have single and multi-dimensional arrays, and also fixed, variable, and max size arrays. Structures, which are pretty typical, maps and containers. You can also have a wildcard type, which is similar to a variant. You can have pods, which are essentially, to explain the difference between a pod and a structure. In a structure, the data is out of band basically, or out of linear memory. So you have pointers to the actual values. In a pod, which is sort of for plain old data, they're all aligned in memory. So it's kind of structure versus like a Python structure where the data isn't actually contained in the structure itself. And then named arrays, which are basically a lot of times in like MATLAB, you have all the data in one single array, but each entry has a meaning, like for a quaternion or a point. So the named array represents that kind of idea of a union between a normal array and a structure. And then of course the enumerations. So the reason for all these different types and members is to try to capture the semantics of how you actually interact with the service as much as possible, and to allow the Robot Raconteur technology to understand what you're trying to do. And we found this to be very effective in our use. So I'll be going through some examples of what these look like as we talk about the standardized interfaces. But there's also the tutorial on the Robot Raconteur website for Python, which goes through kind of getting started with how these all interact. So I want to talk about standardization. and I did not include it in these slides, but these standards did not go through a full committee as you would typically do. I think that the most reasonable group would have been the object management group, but the membership fee is like $11,000 a year. So Matt, I actually want to mention to you that I think that one area that we may want to look into is creating like an open source standards group, which does a much lower barrier for entry, because right now the ones available for this type of technology are pretty arduous to get into. So a group like IETF for the internet is pretty low key, and I think that anybody can submit a standard and people just discuss them rather than having to go through such a high barrier for entry to standards. So that's something to consider for this group. So there are 2 tracks of standardization we looked into, and this is done during the ARM project. This is some of our deliverables. So the 2 tracks for standardization are standardization of the actual Robot Raconteur technology and the standardization of the service definitions to talk to devices. So the link there goes to the standards for the technology itself, which is kind of out of scope for this discussion. That's kind of low-level stuff, like the object and value models, the syntax, and the transports and binary protocols. These are all available for review there. And then there's the service definitions, which are used to create interoperable services, which have the same or have shared capability. And as I said before, if you have a client that understands the service type, it can connect to any service which provides that type. And these standard service types are designed to be generic enough that multi-device within a class can use the same device or use the same type. And these are extended through inheritance using polymorphism and object-oriented to the techniques. And you can also have proprietary interfaces on top of the standard ones while still maintaining compatibility with standard types. So currently the most used type is the robot interface, and it provides feedback on the state of the robot and allows for command modes. And this is designed for like externally controlled robots, like examples are ABB EGM, the Sawyer robot, the UR with RTDE. So these are externally controlled robots. Our current project is looking more into using the onboard motion controller. So we have a motion program execution that we're working on right now to basically send down a binary instruction file, and then the robot will run that file using a kind of customized interpreter written in Rapid. So that'll be available in the next few months. The goal being that you switch between the onboard motion controller and the external position control. So this controller, this basic controller is based on an abstract robot, which implements a robot type. And it allows for 5 command modes, which are jog, home, trajectory, which will execute a arbitrary path, velocity control mode, and position control mode, which are both real time. So in terms of standard definitions, we have a total of 45 files defined with a large number of types. And we froze group 1 on April 5th, 2021. And again, unfortunately, we did not go through a standardized or a typical it does not have a typical standards group process, unfortunately, but hopefully as we improve these standards over time, we'll hopefully be able to build up that that committee, and maybe the ROS team can help with that process as well. This is just a quick list of the various files we've created of the different service types. So of course we have the robot over here, all the robot types. We also have imaging, which is here, and the geometry, which is kind of just generic or more common geometric types like points and poses and other stuff like that. clocking, device metadata, actuators, all kinds of
John?
interesting stuff. Sure.
I'm sorry,
Yep.
there is a question. Does the file need to be a complete program? Can you stream native commands to the robot instead?
Yeah, can we hold that to the end? I think we'll cover some of that as we go further
Oh, okay.
through the slides. Yeah. So let's talk about identifiers, which is one of the service types. So this is a very short file. So this is actually the entire service definition file for the identifier. So you can see that you start with the command service, which gives the name of the service, the version of the standard type you're using. So this is for the file standard, not the version of the file. And you can import another service definition and then have a using statement for a type, and then define the actual structure here. Now, for those who aren't familiar, a UUID is called the Universally Unique ID. And it's a 128-bit number, which is a number with a 5.3 to 10 times 10 to the 36 possible values. And the idea is that this number is so large that a random value will basically always be unique. Now, of course, there's always the 1 in 10 to the 36 chance it won't be unique, but for all intents and purposes, it is unique. So they're widely used in computer systems all over the place for this reason. You don't need a central authority to create unique IDs. So for Robot Raconteur, the identifier is a combination of a name and a UUID. The UUID shall be unique, while the name may not be unique. And the idea is that this allows you to have to use a name in a laboratory small scale environment. So if you're just working with a device on a table, you can just call the name of the device, or use a UUID in development conditions. So you make sure you talk to the exact device you want to. So there are matching rules that you try to match both first, the UUID and then the name. You can, if the name is empty, that's a wild card. If the UUID is empty, that's a wild card. So this is one of the fundamental types used in the standard interface types to define the metadata information. And here's an example of geometry. This is, of course, excerpts from the service definition, not the whole service definition. So these are named arrays for stuff like point, quaternion, and pose. So these are all stored as a flat array in memory and in transport. And you can actually in C, in C++, you can get to these as either. And for instance, in NumPy, these are stored as in Python, these are stored as NumPy structs. And they can also be mapped in memory using the view command to arrays. So as I said, these are union types. And then you have a structure. These all have to be the same underlying primitive type. So these all have to be doubles. And then the pose just stacks these in memory. The name pose is a structure, which is, as example, using an identifier for the parent frame and the frame of the pose, and then the pose itself. So as I said, structures, the memory is not local to the actual structure, while named array, it's all flat in memory. And here is the device metadata structure. So this is the first object you've seen. Basically, all of the device implementations we have implement device. And that has a single field or single property device info. And this contains lots of metadata about the device itself. And this is kind of an aside, but the services also have a attributes field, which is not part of the object. And some of this data is included in the attribute field help of discovery as well. And this has stuff like the device, if there's a parent device, if it's like a conglomeration of different components, a manufacturer, a model number, capabilities, options, serial numbers, descriptions. So this is all the metadata which is passed to the client, so you can interrogate to figure out what it is. And for different devices like or different device types like a robot, we have another more another type of more info called robot info, which contains stuff like kinematic data, which is another field in the object. We also have some clocking defined. Now, this is not as developed because you've never actually done a project requiring high precision clocks. But essentially, this is trying to capture a lot of metadata about the clock and also capture like the fact that in a device, you typically have a time spec, which is like a steady clock with a performance counter. And then like a real-time clock, which is probably less precise, but is actually set to a external source like NTP, and a sequence number, which is usually a counter on the number of cycles you've gone through in that device. Now, the way we handle rates within the system is that we have something called the isochronous device defined here, which you can receive metadata about the clocking, and then you can downsample per client. So you can say, all right, only give me every 4 samples, and then that will reduce the rate of data transmission from the service. And this contains more data about the isochronous device itself. So the update rate of the system, the ISOC epoch, which is like the starting point of the isochronous counter, and then the downsample, the max downsample available. So as I said, this is a little bit less defined, so we haven't done much with high precision clocking, but this assumes that you're using external synchronization methods such as precision time protocol. We're not going to get that low level we worry about clock synchronization on the network level, because that requires specialized hardware typically. And this is the robot structure. Can you guys read this, or is it too small?
I can see it.
Okay. Unfortunately, robot structure is kind of verbose, so it's difficult to show on a slide. So as I said, this is an external control mode for the robot. And I'm just going to go through it kind of quickly because we're running a bit short on time. So essentially, you have the types implements, the metadata here. You change the command mode of the robot between jog, home, position, velocity, and trajectory. You get data from the robot of what it's doing. Enable, reset, disable, etc. The jog commands here. Executing trajectory, and this uses the generator to do long-running operations. So you call next every few seconds to continue the motion. And this is a way to deal with timeout issues and also to pass data back from the trajectory execution. State information. And then there's a pipe, there are wires for real-time data, and then a pipe for logging, which does not drop packets. Isochronous control, clocking, and then wires for position and velocity commands. Homing command, and then just some generic functions for signals and tools and payloads and parameters. This is what a robot looks like. And we have the state structure, which is the data passed every time step or downsample time step to the client. And then the 2 metadata structures containing the different, more specific information about the robot. So this data from here is interrogated by the client to determine how to interact. So like for our teachment, it can look at the structure and actually automatically load the kinematics in from the robot driver to interact with the robot. And typically right now we use a YAML file on the driver side to fill this data in. And one thing I want to mention is that all of these structures have this extended field, or most of them do, for metadata. And this is a wildcard field to stick new data I didn't think of when I created the types. So this is a future proofing step for the standard types. And most of the structures have this extended field, except for something like robust state where it might be a performance issue. So we also have a standard, well, the interface itself is not standard, but use standard types for Gazebo. And that allows you for extensive API access into Gazebo itself. And we have standardized drivers which talk to the plugin. They run as separate processes and they expose standard types. So we have the simulator, which is basically indistinguishable from real devices to the Teach Pennant and other clients. So we use this a lot for development use. And I also recently added the iRobot Create as another scene in the train simulator, which matches the tutorial. So you can run the examples now in Gazebo rather than needing a robot. So now we have how does Robot Raconteur and ROS work together? Well, ROS can mean different things. So ROS can mean a collection of libraries and meta operating system, in which case we use it all the time, right? We use tons of libraries in ROS. And Robot Raconteur itself is available in ROS now. Now, ROS as a pub sub is a bit more complicated, you know, as a middleware. So we have the ROS-II bridge, which allows you to have a general purpose access to ROS-II from Robot Raconteur. And we also have the issue where you have device specific proxy drivers. So for instance, for the Sawyer robot, which is a ROS native robot, we have a driver which exposes Robot Raconteur interface, but then talks ROS on the back end to the robot itself. And we found that to be extremely effective where we use ROS as an inter-device middleware. So, you know, for Robot Raconteur, device may be a bit of a higher level concept. So we use ROS to communicate inside a device. So, you know, behind that standard type, there may be a couple nodes talking to each other. And this allows to have, you know, device specific interface rather than having something like the bridge, which is just sort of a way to peek and poke different services and topics in ROS-II. And there's also the reverse where you can have ROS nodes that talk to a Robot Raconteur service, but that can be a little tricky because, I mean, as you can see, the types are kind of verbose. It's not entirely clear to me how you would digest this down into a ROS topic and service, but that's definitely something we're talking about. So how does this fit into hardware working group? So developing and maintaining drivers for proprietary devices is very challenging. And it's kind of a cat and mouse game with vendors trying to convince them to either not change stuff or chasing them. So this is a problem for everybody, but especially for a small team to try to keep up with the proprietary vendors. So the question is, can we share the development efforts so we're not duplicating? And of course, I will contribute as I can to this process. But the problem for me is how do I access the ROS-II hardware backends? So the way we do it now is that for ROS-I or ROS-II, the nodes in Robot Raconteur run in different processes, which is really slow and has a lot of performance penalties I don't really want. Then there's also the idea of using ROS-II components and Robot Raconteur in the same process, which is better. And then there's also the idea of using Robot Raconteur to kind of intercept RMW library commands rather than going through RMW itself, which may be better. And then the best is to have a standardized API or plugin architecture so that, you know, there's just a library for each device you can talk to. Now, the biggest penalty right now for a modern computer is actually context switches going between threads. So the only one that avoids that problem is to have a standardized API where you're not switching threads to talk to a device. And that's actually why a lot of microkernel architectures and microservices fail, is that the context switch is too much of a penalty in order for it to work. So that's the reason we still have a monolithic kernel in Linux, is it because of that context switch. So that's something we really have to keep in mind developing these drivers, is how do we avoid that context switch? And that's why I think that having a plugin system or API is extremely important, not just for me, but for future devices to be able, or for future users to not have to worry about that penalty of the going through serialization, and even more so that context switch. So the other thing that I wanted to talk about a little bit, not today, but at some point, is functional safety and real-time support. And tangential to that is the fact that Linux networking in preemptive RT is not real time. I've seen a lot of people using it that way. It's not real time. There are some options to get real time, but the only project I've really seen do a good job of that is Machine Kit. So that'd be a good inspiration to look at is how they do it. And maybe we should build some stuff on Machine Kit. I know that Tormac is using that, so they've done some interesting work. I know that Swear has done a lot of work with Tormac on that. So that's just something worth looking into and keeping in mind when developing these drivers. In terms of related future work, the core library is close to version 1.0. A few more things on the punch list to get done. I want to have it at quality level 2 when it's released 1.0. It was going to be this year, but ironically, I have too much work with these projects spinning out, so maybe a little bit later. There's a few more implementations in C# and JavaScript and in ANSI C I'm going to be working on, which are a little bit less priority. Now, there's also Robot Raconteur Quick, which is using the new Quick protocol, which is the new standard for web browsers and everything else in the internet. So again, that's a discussion another time. Continuing development of drivers in Teach Pendant and improved viewer based on 3GS. So this is what I've been using for the viewer and Tesseract for the Python side. And this is actually mainly intended for use of the Teach Pendant, which is web-based. So I'd be interested in suggestions on that. I know there is some older ROS-based 3JS stuff, but I wasn't really seeing maintained. So anyway, that's another discussion. Mobile robots, I haven't done much of mobile robots, so adding standard types and drivers would be good. And then a couple projects under consideration, Murmuration, which is an idea for a fleet management system. And this would be more like an IT platform rather than ROS launch, which is kind of like a launch and done type thing. The idea is I want to be able to start and stop processes, add and remove them, distribute credentials, aggregate logging. So right now, Robot Raconteur doesn't have like a good option for that. So I think it would be useful for ROS2 as well. So if people are interested in that, let me know. And also, can you use Robot Raconteur as a middleware for RMW? So that's definitely something to think about. I think that you can have a lot of the features of Robot Raconteur available to nodes passively if that's part of the middleware. And you can also imagine a situation where there are like these device-specific drivers are injected into the middleware side so that if you spin up a device with the appropriate typing, it will be able to just automatically provide the proxying to that device. That's part of the ideas for how to communicate with ROS2 drivers from the previous slide. And then of course, there's just a honorable mention for the Tesseract Python wrappers. I haven't given it a try. There's a short tutorial or short example to spin up and take a look at. So that's it for me. Let me answer that question that we had in the chat.
Yeah, it's in the chat.
Can you stream native? Yeah, so the question is, does the file need to be a complete program? Can you stream native commands to the robot instead? So the problem we're having with the native onboard commands is that the update rate is really unpredictable. So sending a command to a robot can have a delay between 10 or 100 milliseconds. So streaming commands isn't always the best option. What we are doing now is we have a it's actually just working on it yesterday. You have the ability to send an entire like sequence of commands to the robot in a file. And you also have a preempt option so that you can have another file which has a switch over. So there's a command number in the sequence where you can say, okay, this command number switch to the new file. And that takes about 50 milliseconds to update. And that seems to be the way to do it, where rather than streaming, you would have the ability to just update the command. And also potentially have the ability to have like an offset you add to it. Now streaming, I guess I could try streaming native commands. I'm interested to hear what your use cases for that.
I've used it before when I worked at Kiba and didn't want to replace the robot controller. Their system for taking in commands, every robot controller has some type of look ahead. So if you've got a robot program with 1,000 movements in it, it's gonna, and you hit start, it's not gonna read all 1,000 movements. It's gonna grab 4 or I think 8 with MotoMan, and then it kind of has to sit there and wait. And as long as I was able to keep those 4 or 8 commands fed, it was just like running a program on the teach pendant.
Yeah, so hang on a second. Change this for the slide capture. So this is the software we're working on now for that capability. And essentially the way that this program works is you have this is not the Robot Raconteur driver, this is just the Python interface. Essentially build the motion programs and then you execute to the robot, and this robot this command will reset the program pointer, start the program, and then run through this file, which is just like a binary opcode based file. Now the thing we're working on now is preemption. So this is this is the initial work on preemption. So essentially you have the motion program again, but then you have a preempt program here, which is like has a certain command number start set, and then the new commands. And then you have in this example, you start the first program, sleep, and then you preempt it with the new program at a certain command number. And then you just cycle through and wait for it to complete. So this is early work, but yeah, you can definitely stream individual commands is kind of isn't great because you don't have much control over what the robot controller does at that level of granularity. But this seems to be working pretty well, where you just can download a new program, and you can do short programs too. You have like 10 or 20 commands per program, and just string them together using preemption, and just select what command number you switch over from one to the other. So this will be in a Robot Raconteur driver at the end of the year, available for ABB, and hopefully we'll have either a standardized type or some plus standardized type for that functionality.
Do you think this command interface you have could be used as a more simple robot post processor? There's that RoboDK post processor library, but it's a little bit clunky and hasn't been updated in many years.
Yeah, so actually this does exactly that. So move back to the other command example. If you look at the printout, it actually, for debugging purposes, we had it so it can generate out rapid code. So we already have that capability now in this driver this isn't a driver, this is just a Python library right now. The driver's coming. But this has the ability to generate out rapid directly from the commands you send to it. So yeah, that's definitely a feature we have. Now we're going to be doing the same thing for MotoMan in the next project. Now, the difficulty for me is I do not own robots. I have a Puma in the basement I play with. I don't have any modern robots because they're ridiculously expensive for a one-man operation to have. So if you want more features on your robot, then, if I can play with them, maybe we can figure something out. But for now, I'm limited to what robots I get access to.
I wonder if MotoMan would spot you their simulation software.
Yeah, they're actually on our project. They joined our team. So we definitely have access to their. Now the problem with MotoMan is that their software is super primitive compared to like Robot Studio. So yeah, Scott was on our new project starting up. We'll be working with the MotoMan robots.
Yeah, not all OEM simulation softwares are equivalent, right, as far as actually representing the behavior of their robot controller. And MotoSim is notoriously limited.
Yeah, Robot Studio is really pretty impressive how accurately, well, quote unquote, accurately it represents the robot. There are, of course, differences in performance compared to the real robot, but they do run the full controller on your PC. And that's been really exceptional for this use case of developing these drivers, because you can really test everything out and catch all the bug. Well, not all of them, but catch most of the bugs in simulation first before you put on the robot.
Yeah,
UR is not bad either in that sense. UR is pretty good, but they're kind of the outliers in terms of simulation capability.
Yeah,
The way Kiva dealt with theirs is it would basically run the controller in a virtual box instance, so you also got similar performance.
I'm sorry, did you say Kiva?
The way that Kiva, their
Okay.
simulation stuff worked is it would basically run the whole Linux-based controller in virtual box. So you wouldn't have real time, but it would work exactly the same for the most part.
Yeah, I'm not familiar with the robots.
Any other questions for John?
There's one in the chat. Oh, wait, never mind. Sorry.
No, I was gonna say, I noticed Dr. Wen noted that you have MotoSim. And then Heish must have had to take off. Well, great. John, I appreciate you taking the time today to share your progress and how you're handling interfaces. I think it's a nice alternative approach to kind of what we've seen in purely the ROS side of things. So I think it drives some discussion and you bring up some good points about, we don't really call it standard orgs, but obviously this notion of reps in the ROS world is kind of a de facto standard, right? And I think it's something that, so we just got an inquiry from some people that are supporting using, ROS projects towards space robotics, right? And so they got a requirement from NASA that their code, any code they contribute and on an SBIR, STTR has to adhere to the space ROS standard. And we're like all laughing because there is no space ROS standard, right? So what does that even mean, right? So I think there's some definitely an opportunity here, and I think open robotics has struggled as people toss around the phrasing that ROS is sort of a standard, or ROS2 can become a robot standard, because they don't necessarily have the rigor, nor do they seem to have the appetite to own anything, right? So yet at the same time, they're very stodgy about accepting contributions if it deviates from their vision. So we've obviously got some work to do here. Like I said, we've recorded the presentation. I'll make it available to the broader community. A couple folks were looking forward to seeing it afterwards. I did try to gather some notes. So for those of you who are interested, check out my notes. I grabbed a few of the slides and I tried to type along here. If I said anything dumb, please feel free to correct the record. It's on the Discord. The link is in the Discord. So John,
two more thoughts actually before we close up, if you don't mind, Matt.
Yeah, sure.
So one I was thinking about is that I like how the IETF works, Internet Engineering Task Force. They're kind of a more open group, less stodgy. So maybe we can create an open hardware task force. I don't know, something more general than ROS, because I think that there's a need overall for open standards which are not going through this kind of huge barrier for entry, like $11,000 to join OMG or something. That's something to consider. The other thing I forgot to mention is that it might be possible to run Robot Raconteur on top of RMW. So, use it as a transport. So that might be another way to standardize, is to just, sit Robot Raconteur on top of the topics in ROS. So two things I forgot to mention during the presentation.
Well, I was wanting to ask.
Oh, sorry.
And what the ROS technical steering committee type of people might ask is, why not just use DDS and ROS instead of having your own structure?
Well, I mean, the short answer is this existed before ROS and DDS are working together. The long answer is that Robot Controller is a higher level interface. So, you could probably use DDS as transport for this without too much difficulty, although the semantics are quite the same with the way the data is handled.
The extensible messages are a good enough argument for me.
Noted, and we've noticed obviously they're already kind of wobbling on the mandate that RMWs should be based on DDS. I think for some of these things, right? Like the fact that was it Zeno or something is proposing an RMW, and somebody as a joke made an RMW on email, right? So there seems to be an OPC has talked about creating an RMW implementation. So we're already seeing some wobbling on the DDS side, just because you have to your point, right, is this whole notion of how you manage the semantics and extending messages and things like that it just sits on top of DDS, right? And DDS just ends up being the transport layer, in which case you can use about anything for transport, right? So, is it really the right solution if you end up having to do all this other stuff to kind of get it to work? So I think it's a worthwhile thing to think about. All right, well, John, thank you for taking the time today and adding your approach and the work you've done to the conversation. I think it's something worth thinking about. I look forward to getting the video out there and driving some additional content. What I might try to do is for meeting 15 is to try to distill some of the key takeaways from the various presentations and see if it's something we can get some sort of like what was good, what was bad, and how do we like move forward, like right in this context of semantics, capturing the semantics and the notion of creating interfaces between devices and non-ROS systems, etc. So stay tuned. We'll be getting together again soon. Thanks again, John. There's no other issues or following questions. I suggest we adjourn. Have a great day, everybody.
Yeah, thanks for attending.
Yeah, my pleasure, man. Thanks.